Okay, so the binomial random variable. The binomial random variable. Okay. Very important random variable. Okay. And this random variable occurs, okay, whenever you do something a certain fixed number of times. Okay, let's say 5 times. So whenever you do something a certain fixed number of times, and each time you do it, it's independent. Okay, and each time you may succeed or fail. Okay, so let me state the sort of 3 basic conditions that come to play when we're talking about the binomial random variable. So 1, okay, you're repeatedly trying something, some fixed number of times, a fixed number of times. Okay, so let's say, say 5. Okay, and each time you try, you can either succeed or you can fail. Okay, so each time, each trial is a success or failure. Okay, and each trial succeeds with probability p. So the same probability p. Each trial is a success or failure, and in each case, the probability of success is p. So for example, p could be, let's say, 1/3. P equals 1/3. Who knows? So that means you're trying something over and over and over and over, a fixed number of times, let's say 5. Okay, and each time you will succeed with probability p. Okay, so it's important that each trial has the same success probability. Okay, and each trial, so condition number 3, each trial is independent. So you keep trying something and trying. Each trial is independent and succeeds with some probability p. And what you are interested in after you have done all your trials, okay, is, how many times did I succeed? So you're interested in the random variable x is equal to the total number of successes. Okay, very interesting. Okay. And you can imagine, you can see how this is very relevant to the real world, right? You get 50 shots at something, let's say shooting a bullet at a target, and each time you randomly try and you'll succeed in hitting the bullseye with, let's say, probability 1 in 10. Okay, so if you shoot 50 times, I'm interested in how many times did I hit the bullseye. Okay, so this is a very common thing, a very common experiment that we do in practice. You get a certain number of trials and you try to succeed each time independently, and you have a success probability p. Okay, we're interested in the total number of successes. But now what's interesting here is that, each success or failure is a binary Bernoulli random variable with probability p. Okay, so the binomial random variable is exactly the sum of a bunch of Bernoulli binary random variables. Let us say that the fixed number of times you try, in this case 5, let us typically in general call it, n. So you have, a Bernoulli random variable x1 plus x2 plus x3 plus xn. So there are 2 parameters that are at play here, okay, in this experiment. Okay. What are the 2 parameters? The first parameter is n, the number of trials I'm giving you. Okay. And the second parameter is p, the probability that you succeed in each trial. Now, let us consider the sort of prototypical, the simplest example, okay, the most common example of such a random variable, which is you just flip a coin, let's say 5 times. You flip 5 coins. Flip 5 coins. Okay, so let's see if it satisfies these 3 requirements. 1, You're trying something a fixed number of times. Yes, you have 5 trials. So 5 trials. Okay. Are they independent? Yes. Okay. If the coins are independent. So we assume the coins are independent. Independent. Okay. 2. Okay. So 3. Independent. Yes. Fixed number of trials, yes. Okay, and is each trial going to succeed with the same probability? So we have to define success. So let's say success is ahead. So is each trial going to succeed with the same probability? And that will be the case if they're identical coins. So typically we will say flip 5 identical coins. So then there's the same probability of success for each trial. Okay, so same probability of success. And P, okay, we'll call that probability of success P, and that P will equal a half if it's a fair coin. But in general, it can be a biased coin, or, in general, we will call it P. So for example, P might equal a third. Okay, so if you flip 5 identical coins, fixed number of times, they're independent identical coins, they're independent, and they all have the same probability of success. And the number of heads, so each of these trials is a Bernoulli random variable, x1, x2, x3, x4, x5. And what we're interested in is the total number of heads, which is the total number of successes. So we're interested in the total number of successes, which is x1 plus x2 plus x3 plus x plus x5. Okay. So let us compute the probability. So what's the random variable x, and what are its possible values? Its possible values are 0, 1, 2, 3, 4, 5. Okay, so these are the possible values. Okay, and let us now compute the probability for each possible value. Okay, and as an example, let's do, what is the probability of a total of 2 heads? Okay, so probability. Okay, so we need to look at all the various outcomes with 2 heads. Okay, so here's an outcome with 2 heads, H, H, T, T, T. Here's another outcome with 2 heads, T, T, H, T, H. Okay, so if we're doing the outcome tree for this experiment, what will happen? So you have your root, okay, and you could go either H, H, T, 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 or in this case you've gone T, T, H, T, H. Okay, so, and there are all the various other outcomes that give you 2 heads. But I just want to illustrate something with these 2 particular outcomes. And remember, these are complex outcomes. Ultimately, we want to just focus on the random variable, which is the total number of heads, which takes on the value 0, 1, 2, 3, 4, or 5. Okay. So let's put probabilities, for each of these edges. So this edge probability, if it was a fair coin, it would be half-half. But now I want to be general. I'm imagining, a probability of success P. And just to illustrate, let's use P equals a third. So we succeed with probability 1/3. So this is 2/3. Okay, this is 1/3, and this is 2/3. Okay, this is 2/3. This is 2/3, and this is 2/3. This is 1/3. This is 2/3, and this is 1/3. Okay, so now when I multiply the edge probabilities, I get 1/3, 1/3, 2/3, 2/3, 2/3. So I get 1/3 squared, 2/3 cubed. Okay. And here I get 2/3, 2/3, 2/3, 1/3, 1/3. So I get the same value, 1/3 squared, 2/3 cubed. That's very interesting. What if it was 1 instead of 1/3? What if it was some general number P, and this was 1 minus P? So then this would be P squared, 1 minus P cubed, and this would be P squared, 1 minus P cubed. Okay? And the thing to observe here is that, no matter how you arrange the heads and tails in this sequence, okay, no matter how you arrange them, when you look at that path in the outcome tree, you're going to have 3 1 minus P's and 2 P's. So all the sequences with 2 heads, okay, will have the same probability of 1/3 squared, 2/3 cubed, or more generally, p squared 1 minus p cubed. Okay, so let me write that down as a conclusion, a sort of reminder, very important conclusion. All sequences with two heads, in the tree have two edges, that are 1/3, and three that are 2/3. Okay, so the probability for that path, when you multiply the edge probability, so the probability for that path is 1/3 squared, 2/3 cubed. And the squared has to do with the fact that there are two successors, two heads, and the cubed here has to do with the fact that there are three tails or three failures. Okay? And more generally, if it was not 1/3, it would be p squared and 1 minus p cubed. Okay? So then what's the probability of this event, that you have a total of two heads? Well, since each of the possible sequences has this probability, then to get the event, I need all those sequences, and then I add up the event probabilities. So when I add up the probabilities of all those sequences, I'm going to add this guy up for each sequence. So in other words, the probability of two heads, which is the probability of, which is the sum of the probabilities for each sequence with two heads, is exactly the number of such sequences times that probability. Okay? So now that's the important conclusion that we need. Okay. The probability of, x equals 2, okay, is equal to the probability to get a sequence with two heads, which is equal to the sum of probabilities for all sequences with two heads, okay, which is equal to the number of such sequences with two heads times 1/3 squared, 2/3 cubed. 1/3 squared, 2/3 cubed. Or more generally, it would be p squared, 1 minus p cubed. Who can tell me the number of sequences with two heads when the sequence length is 5? That's just the same as the number of binary sequences with two ones. This is just 5 choose 2. Okay, that is just 5 choose 2. Okay, so here I can plug in now. 5 choose 2. 5 choose 2. Okay, 1/3 squared, 2/3 cubed. Okay, so as a quick pop quiz, what am I going to plug in here? So what's the probability of 4 heads? Okay, so pause the video. 1, 2, 3, 4, 5 seconds. Okay, if you're coming back and you said 5 choose 4, okay, 1/3 to the 4th, 2/3 to the power 1, bam! You got it right. Okay. So each such sequence has 4 heads, so you're going to have, 4 heads in your outcome tree. So those each have probability 1/3 to the 4th, and then you have one tail, so that has probability 2/3, okay, to the 1. And the independence is crucial because that's what allows us to multiply probabilities for each of the individual coins. Okay, so now let's just give the general argument when you do this experiment in general and then do an example. Okay, so in general, you are going to try something n times, and the success probability is p. Okay, so let's make the same argument. Try n times, and success probability is p. Okay, you try n times and the success probability is p. And we are interested in, the probability that you get a total number of successors k. So the probability that the total number of successors, so this random variable x which adds up the number of successes. The probability that the total number of successes is k. Okay. So let's look at one such sequence that has k successes. If we're, let's say, in the world of tossing coins, so it's going to have, okay, so the simplest such sequence with k successes has the first k heads, and then the remaining k are tails. Okay, so there are k of these, and how many are there of these? And this is where the number of times you try becomes very important. How many are there of this is exactly n minus k. Okay. So now when you do the outcome tree, or you can just view it as from the point of view of independence, this happens with probability 1, p. This is p, this is p, this is p. So this is p times p times p times p. And then this is 1 minus p times 1 minus p times dot 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 times 1 minus p. Okay, so there are kp's, so we get p to the k. Okay, and there are n minus k, 1 minus p, so we get 1 minus p to the n minus k. Okay, so any sequence with k heads and n minus k tails has this probability. So the probability that x equals k has to add up the probabilities for all the possible sequences with k heads. But we know how many there are. There are n choose k sequences with k heads times the probability of those sequences with k heads, which is p to the k, 1 minus p to the n minus k. Okay, so this is the number of sequences with k heads, and this is the probability of one of those sequences. Okay. And so now we can fill in this table, okay, but we're going to fill it in for another example. Okay. So this is called the binomial distribution. This is called the binomial distribution. Okay. And this random variable is called the binomial random variable. Okay. And it satisfies these three conditions. Fixed number of trials. Each trial has a success probability p. The trials are independent. You are interested in the total number of successes. Okay. And we would like to know what's the probability of 0 successes, what's the probability of 1 success, 2 success, and so on. Okay. So I will rewrite that formula here now. The probability of k successes, which is the probability that x equals k, is exactly n choose k times p to the k times 1 minus p to the n minus k. Very important formula. And why is it a very important formula? It's because that process where you try something a fixed number of times and wait eagerly to see how many of them succeeded, that process is an experiment that we do very often in practice. Okay. Okay. So, let's do an example to show you how common this process is. An exam has 15 multiple choice questions. Okay, with 5 answers per question. 5 answers per question. Okay, so your strategy on this exam is to answer randomly. Okay, so you answer each question independently. So none of the answers in one question are going to influence whatever you do in the next question. So you answer the questions independently, okay, and you're going to answer randomly. So let's see. I claim that this is a binomial. So now you're interested, of course, in how many questions do you get right, okay, with this interesting strategy. And I know some students like to use the random strategy in my multiple choice tests. Okay, so I claim that the number of questions you get right is a binomial random variable. So let's see, does it satisfy these 3 conditions? Condition 1, you're trying something a fixed number of times. So yes, and how many times are you trying? 15 times. 15 trials. So n equals 15. Okay. 2, is the chance of success in each trial the same? Yes. Why? Because you're trying each question independently and randomly, and you answer randomly. So, and since there are 5 answers, your chances of getting a question right are 1/5. So P equals 1/5. Oh, nice. Okay. And then, is each trial independent? Yes, that's the way you're choosing to approach this problem. Every question you're going to answer independently. So 3 independent trials. Okay. So, given this, the probability that you get K right is equal to 15. Choose K. Okay. 1/5 to the K times 1 minus 1/5. 1 minus 1/5, which is 4/5 to the 15 minus K. So let's see what that looks like. So let's draw the PDF for this random variable, random test answering. Okay. So number of successes, let's call it K. Okay. And K can be either 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so let's work out these probabilities. Boom, 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 boom. Well, you just plug in different values of K into this formula, and so I'll just tell you, what we get. Okay, so probability. Okay, so your chances of getting nothing correct, it's actually non-trivial. Okay, it's about 4%, approximately. These are now approximate numbers. The chances of you getting 1 correct is approximately 13%. 2 correct, 23%. 3 correct, 25%. 4 correct, 19%. 5 correct, 10%. 6 correct, 4%. 7 correct, 1.5%. 8 correct, 0.3%. Okay, and then basically approximately zero. Okay, this is about 10 to the minus 4, so this is about 0.07%. Okay, and then your chances of getting 10 correct are 0.01%, and 11 correct are 0.001%, and then 0.0001%, and then 0. I'm just gonna say 0. Okay. So let's look at this random test answering strategy. Okay. The most likely outcome is that you get 3 correct, 25% of the time. Okay. What about passing the exam? So if passing is defined as more than 50%, so then you need to get more than 7 correct. More than 7 correct is the sum of all of these. And the sum of all of these is approximately 0.4%. So 99.5, 99.6% chance of failing the exam if you answer it randomly. If it was 15 multiple choice questions with 5 answers per question. So don't answer these kinds of questions, randomly. It's not a good strategy.